Welcome to the Digital Logic and Design series. In this module, we will explore the essential concepts of low-power design and various techniques used to reduce power consumption in digital circuits. Let's begin by understanding the importance of low-power design and its applications in modern electronic devices. Low-power design is crucial for several key reasons. Firstly, it extends the battery life of portable devices like smartphones and laptops, allowing them to operate for longer periods without needing a recharge. Secondly, it reduces heat generation, which is essential for preventing damage and improving the reliability of electronic components. Thirdly, it leads to cost efficiency by lowering energy consumption and reducing the need for expensive cooling solutions. Lastly, it minimizes the environmental impact by decreasing overall energy usage. Power consumption in digital circuits can be attributed to three primary sources. The first one is dynamic power, which is consumed during switching operations when logic states change. The second one is static power, which is consumed even when the circuit is idle due to leakage currents. The third one is short circuit power, which is consumed during the brief periods when both PMOS and NMOS transistors are conducting simultaneously. The total power consumption is the sum of these three components: dynamic power, static power, and short circuit power. Dynamic power is a significant component of total power consumption. It can be calculated using the formula P dynamic equals alpha times C times VDD squared times F. In this formula, alpha represents the switching activity factor, which indicates how frequently the circuit switches. C is the load capacitance, which is the capacitance that the circuit must charge and discharge. VDD is the supply voltage, and F is the clock frequency. Voltage scaling is an effective method for reducing dynamic power consumption since power is proportional to the square of the voltage. Dynamic voltage scaling, or DVS, involves adjusting the voltage based on the performance requirements of the circuit. Multi-VDD design uses different voltage levels for different circuit blocks, optimizing power consumption for each block. Adaptive voltage scaling involves real-time voltage adjustment based on the workload, further enhancing power efficiency. For example, reducing voltage from 5 volts to 3.3 volts can significantly reduce power consumption. In fact, let's define a small program to demonstrate this. It will calculate the power reduction when voltage is reduced. It takes old and new voltage values as input, calculates the ratio of new and old voltage squared to get power ratio. This is used to find the reduction. The reduction is the difference of 1 in power ratio, multiplied by 100 to express in percentage. Clock gating is a technique used to disable the clock signal to unused circuit blocks, thereby reducing dynamic power consumption. By preventing unnecessary switching, clock gating can significantly improve power efficiency. In terms of Verilog implementation, here's the clock gating cell. This module takes clock and enable signals as input and outputs a gated clock. The gated clock is simply the logical end of the clock and enable signals. So when enable is low, the clock is blocked. When enable is high, the clock passes through. Power gating involves shutting off the power supply to inactive circuit blocks to minimize static power consumption. Fine-grained power gating allows individual logic blocks to be powered down independently. Coarse-grained power gating involves powering down entire functional units or cores together. Sleep transistors, which are high VTH transistors, are used to control the power supply to circuit blocks. In this Verilog code, the power gating controller is described. When the idle signal is detected, power enable is set to 0, and sleep mode is activated. When the wake request is received, power enable is set to 1, deactivating the sleep mode. Low-power logic design involves optimizing the logic implementation to reduce power consumption. Logic restructuring minimizes switching activity through optimized logic paths. Gate sizing involves using minimum-sized gates to reduce capacitance. Threshold logic utilizes multiple threshold voltage transistors to achieve a power-performance trade-off. For example, this is a high-activity logic statement. Assign out 1 equals A and B and C and D. Here, it is restructured to low-activity form as shown here. Assign temp equals A and B, and assign out 2 equals temp and C and D. This reduces switching when A and B are 0. Memory power optimization focuses on reducing power consumption in memory subsystems. Memory partitioning divides the memory into banks that can be powered down independently. Data retention modes reduce voltage while maintaining data integrity. Cache optimization uses way prediction and subbanking to reduce access energy. These memory banks can have different power states, such as active and sleep. In summary, low-power design is essential for modern digital systems. Key power reduction techniques include voltage scaling with dynamic voltage scaling and adaptive voltage scaling, clock gating, power gating, logic optimization, and memory management. The impact of these techniques can be significant, with dynamic power reduction ranging from 50 to 90%, battery life extension by 2 to 10 times, and heat reduction by 30 to 60%. By combining these techniques, we can achieve significant energy savings while maintaining performance requirements. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.